All right. Hello, everyone. Welcome to Friday MenChem. We're going to talk a little bit about drug optimization today. Before we get into that, I want to mention we've got one more person taking the exam today, and then we have a little more grading to do, and then we should hopefully get them to you by Monday or Tuesday. They're looking pretty good. I think you guys are in the running for some donuts, which is great news. For anyone that's reached out, you guys really appreciate the emails about me maybe not feeling so good. I'll tell you all, it is medicine induced. So I'm okay. I'm gonna make it. We'll be back at it in person on Monday. Yeah, lots of positive vibes coming into just want to let you guys know we're gonna start a tradition, start it back up. You guys can put in, something positive that's going on in your life over the weekend, just to share a little good stuff before the weekend. Very interesting. Okay, cool. We're gonna go ahead and get started, and I'll revisit this to see if there's any sort of questions a little later. So last time, we were talking about sort of these drug leads, how we access them, etc. And so let me is there someone speaking up? No, just a little flutter. Okay. Okay, yeah. So today I want to talk to you guys a bit about drug design and sort of optimizing drug interactions. And so this is where you start to, really become, some medicinal chemist on sort of a structural level, which I think is really, really neat. This is arguably one of my favorite sort of lecture parts to give. So we'll go ahead and we'll talk about that. Again, it's going to be very similar to sort of what you saw in the first part of the course, only we're going to talk about it sort of now that you have a little bit of background about medicinal chemistry. Talking about sort of how we capitalize on sort of functional groups on a molecule to go ahead and optimize interactions. And so, yeah, to get started, a lot of this, begins with sort of, thinking about structure activity relationships. And these are, as it says, on sort of the top definition here, the identification of the parts of the molecule that are important to the biological activity and those that are not, right? So we talked about last time, if you can, you want to try and, come up with sort of the most simple molecule you can, right? That's going to sort of go after whatever sort of biological response you'd like it to. And so, and the reason for that, often is very much tied to synthesis, but also, it also has a little bit to do with, thinking about, the more functionality where you put on a molecule, right, there's a good chance it can get to sort of off target locations. And so a lot of this comes down to sort of the addition or removal of molecular components to see what's necessary for activity. What you're going to find throughout this section is that a lot of that has to do with sort of feeling out the active site or the binding site that you're after. So what a lot of medicinal chemists will do is they'll start with a structure and then they'll start to modify it and sort of tweak it. And we'll talk a little bit about that as we go through. And so this is a good sort of example, right, with glypine here, right? So you have, sort of the starting molecule, right? A few things that you should automatically be able to identify, right? It has some van der Waals type of interactions that it can make, right? Some more van der Waals up here, maybe some even in this sort of core structure. And then, it has some hydrogen bonds and hydrogen bond donors and acceptors here in sort of these phenols, right? And then it has this charged amine, right? Which is also going to play a role in binding. And so, when you immediately look at that section, right, you think, sort of along the lines of, how can we rip away some of the, how do we tell, like, for example, if this portion, this alkene is really important. And how you do that is you start to modify the compound. So you say, okay, if that's important, then if we take it away, right, then sort of, its binding, or it should go down, or it should become a less sort of potent binder. And the same with sort of these charged amines, right? These are easy to modify, such that you can, they can either be protonated or deprotonated, for example, or, in this case, right, they've taken out a methyl, right? So they take out sort of steric components heading into the binding event. And then, then you have this sort of situation, we talked about those phenols up in the top right. You also can start to take away those type of interactions. So you take away a donor, right? If you put on sort of a methyl group, for example, So you basically cap that, right? So you still have a hydrogen bond acceptor, but you don't have a donor, right? You take away those. And so those are sort of the types of modifications. This is sort of a, sort of a, sort of a broad overview of what we'll be thinking about, but we'll talk about that sort of in a little more detail. So I'm going to go through sort of the functional group by functional group to kind of give you a feel for the types of things that you should be looking out for. So, one of the first ones, of course, is the alcohols and phenols, right? These alcohols play a huge role. You guys have seen them, extensively throughout, several different lectures now. And yeah, and they're often involved in hydrogen bonding. And so, typical branching point would be to synthesize the ether or ester analogs. Once again, I will not at all ask you, how do I go ahead and put a methyl group on the molecule, but I will ask you, okay, this molecule has an alcohol and, maybe you want to take away a hydrogen bond donating ability. How would you do that? And you would draw me the structure just with a methyl group on it or something along those lines. And so, typically, right, the way to take away that hydrogen bond donor is to add sort of an alkyl substituent, create an ether, or alternatively, you can turn that into an ester. Now, the thing you want to keep in mind, right, when you make that modification is that now you have sort of two positions, right, the oxygen, or actually both of the oxygens in the ester that can contribute to accepting, right, in sort of the hydrogen bond interaction. So you see some nice examples here where you have sort of the hydrogen bond in sort of panel 1, and then you take that away by heading over to number 2, right? That one is now, right, the ether, taking away the hydrogen bond interaction with oxygen, the carbonyl, I should say. And then the bottom left, right, you have it acting as an acceptor, right? And so now something to think about is, okay, so if it might still function as an acceptor, right, in the event that the alkyl group that you put on it is not too large. But the other thing to consider is sterics, right? Sterics are always going to play a large role in this, right? So whether or not the molecule can actually fit. And so, for example, right, it's representing in number 4, where you've sort of created this sort of steric shield, for example. We'll talk about how to sort of design these as we move along. And then sort of this is the example sort of for the ester, right? So it's always important, right, to remember that there's sort of an electronic factor, right, affiliated with moving to an ester, in that you have these resonance forms. And I would emphasize again that you definitely want to sort of take some time and really rationalize, sort of what these arrows mean. I think in going from, let's say, the left structure to the right structure on the top right, just to get a feel for, drawing resonance structures. You'll have to do that a little bit in your exam. But yeah, right, then you have this sort of situation very similar to sort of the last slide, where you have like this steric shield type of situation. Now you put something on there that's a little bit larger, right? So that's definitely going to come into play. And so we'll talk about sort of how you go about putting something on the molecule that is approximately the same size, but sort of is able to change sort of the hydrogen bond donating or ability of the particular functional group. Heading over to aromatic rings. These aren't going to play a huge role, I think, for you in terms of really rationalizing binding in a binding site or an active site. But what I will say is, right, they're always, they're chalked up to being able to create really good van der Waals type interactions. So they interact well with sort of hydrophobic regions of the active site. And that's sort of very similar case, I think, with sort of like cycloalkanes. Like this is, I don't know if you guys remember drawing a chair, but cyclohexane is also one, right? And that these sort of H's sort of can do that as well, but it doesn't do it as well as sort of the aromatic ring on the top right, or on the top. Ketones and aldehydes are something to sort of consider as you're thinking about sort of designing a drug, right? So, right, they have these, these groups that sort of make for sort of an inherent sort of dipole in the molecule. So in the top, right, you see with an alkene or an alkane, right, both of those sort of are able to form sort of favorable sort of hydrophobic or van der Waals type interactions with the active site, but sorry, I'm trying to let the just add. There you go. But then sort of on the bottom, right, you have this ketone that now has an inherent dipole with it, right? So you're able to capitalize on sort of, anion, ion dipole type interactions, for example, or be able to align the molecule such that it sort of is more favorably able to bind to the active site. Right. So, right, these carbonyl groups, also can function sort of as, hydrogen bond acceptors. And then also, right, on the, sort of, you can imagine, right, if you're able to, you were to then subject this to, if you were to replace that ketone, for example, with an alcohol, right, then you have a situation, right, where you have this sort of tetrahedral structure in the top right. And you can sort of take that, depending on the enantiomer, right, that you get, right, the one that goes towards you or away from you, you're able to sort of adjust, whether or not you get sort of a hydrogen bonding interaction with the binding region of the protein. Carbonyl, yeah, so this is sort of a very similar type of thing, where it's being shown sort of on the bottom, right? You have sort of this dipole interaction, and you sort of really rip away that dipole interaction when you move over to the alcohol. You could argue that there is sort of a dipole interaction with it, and I think that'd be okay, but it's not as strong as when you have a carbonyl there. Yeah, so we talked about before, right? Amines are going to be really important as we move along, and the reason for that, right, is they sit in sort of that pKa range, right? That sort of enables sort of a protonation, deprotonation, sort of tailoring itself to being able to, cross barriers when it needs to, and not cross it when it doesn't need to, for example. And so, right, they're great hydrogen bond donors and acceptors. Ionic interactions are really important also for ammonium ions. And so you see sort of in the top left, this tertiary amine and secondary amine, right? So you have, by switching to the secondary amine, right, you've introduced now a hydrogen bond donor, right? And when you don't have that H, right, that hydrogen bond donation is not there, right? So they're sort of a really easy way to tune whether you have hydrogen bond donation or not. Primary amines, right, are going to provide sort of two hydrogen bond donors, something to keep in mind. But then on the right, where you have sort of these ammonium type species, right, where you have a great hydrogen bond donor, right, in that the nitrogen is charged. A really good hydrogen bond donor again, right, each time, right, because it's charged. But here you have sort of with the secondary amine on the right, you have two, right, hydrogen bond donators. Keep in mind, right, that once you've taken off one of those H's, it's now neutral, right? So it becomes not as good a hydrogen bond donor, but it still is a good one. And oftentimes, we talked a little bit about sort of directionality in the active site or the binding site, and those will play a role, right? These sit very sort of tetrahedral like, very similar to sort of that tetrahedral intermediate. So something to sort of keep in mind as you start thinking about this. The ammonium ions also on the bottom, right, play a role sort of on in performing sort of ionic type interactions. So you have this sort of charged amine, right, with the charged carboxylate in the binding site. So of course, it's a really strong interaction as we learned before. Amides, right, are very, very similar, I would say, to esters, right, but they have the ability to not only function as hydrogen bond acceptors, but also donors, right, because they have sort of the free NH bond, and I'll talk about that in just a second. But so right here, right, you have the tertiary, what's considered sort of a tertiary amine, right? So that amine is sort of fully substituted. Okay, but then if you move to a secondary amide, sorry, that was an amide, the first one. But anyway, so you move to the secondary amide, and now you've replaced one of those R groups with an H, right? So now you've introduced a hydrogen bond donor, right? So these are sort of the types of ways that you'll sort of tune the molecule as you start to design. Then if you move to sort of the primary amide, right, again, you now introduce yet another donor, right, and another H. Again, right, very similar to what you saw with the esters, right? It's important that you sort of take a look at sort of what the resonance structures look like for amides, and they all sort of go through, regardless if it's primary, secondary, or tertiary. They're all going to sort of sit in this sort of resonance equilibrium. So that's something to keep in mind. Another tunable sort of portion is, you can imagine if you were to, let's say you start with with an amine, and you didn't have sort of the carbonyl component on it, right? Another space to sort of play in sort of the sterics realm would be to instead of the methyl off of your, let's say, tertiary amide, you could put sort of larger groups off of that. I also recognize as I'm buzzing through this that you guys are not like experts in doing this yet, but you'll have lots of practice to sort of get the hang of things. Yeah, so this is sort of where it gets to be pretty cool, right? So imagine you go in and you're like, okay, this drug has an amide. It's this design drug that we've come up with, but we don't know, it's got a ton of functional groups. So it's got an amide, it's got an alcohol, it has, maybe sort of just a primary amine. We start to ask, well, okay, what kind of a role is the amide playing? And so what you usually do is you'll start to diversify a library of derivatives of that, where we'll start to say, okay, well, how important is the interactions that the secondary amide provides, right? So for example, you would anticipate the secondary amide in the top left is able to be both a hydrogen bond donor and an acceptor. And so what you start doing is say, okay, well, let's take away a donor. So what you do is you replace that H with a methyl. So then you're like, okay, well, let's do the opposite. I want to take away the donating ability of the accepting ability of that oxygen. So what you'll do is you'll take that out and you'll change it to the secondary amine. And then you want to do sort of the combination of them. You'll change it to this N-methylated tertiary amine. Then you want to rip out the nitrogen. How important is the nitrogen? You start to say, okay, we're just going to rip out the nitrogen and we'll make that a ketone. But then you continue to do that and you'll start to sort of replace the amide with things that are approximately the same size, but also test for how important in each of those interactions is. And so that you can move on to things like an alkene, the primary amine, and the carboxylic acid. That starts to be like, I think really fun as you guys get going. Quaternary ammonium salts, sort of talked about these before. I mentioned a while ago that these are not going to be particularly important interactions, especially the bottom one. I would say the ionic bonding, of course, is going to be important, but I would say the sort of induced dipole interactions with the phenyl groups, I wouldn't worry too much about that. That one's not one that they capitalize on a whole lot in medicinal chemistry anyway. Carboxylic acids, right? You can continue. You guys can probably start to see the trend. You continue playing the game, sort of with each of the different types of functional groups. So carboxylic acids, right? We know, right, they can act as hydrogen bond donors or acceptors. So that sort of allows for ionic interactions as well, right? If it's deprotonated in the bottom. So something to consider with these, right, is that you're going to be able to sort of modify this in many different ways. I think it might be actually on the next. Yeah. So this is on the next slide. So basically what you can do is you can start to say, okay, how important are the interactions with the carboxylic acid? And these are the types of things, right, with the amide as well as the carboxylic acid. I would take a few minutes and just sort of start to think about how to rationalize this a little bit. So with the carboxylic acid, for example, right, you want to rip away or if you want to take away one of the hydrogen bond donating ability, you can go ahead and convert it to an ester. Again, you can go ahead and take off the carbonyl, right, and make that thing a primary alcohol. If you want to say, okay, well, what if we want to introduce yet another, hydrogen bond donor? What you'll do is you'll replace it with the primary amide, right, that has the capability of, providing 2 hydrogen bond donors. And then you start to think, okay, well, how important is, that OH? What if we just rip away that OH? To take sort of the oxygen with the H, right? You can switch it over to the ketone. But then from there, right, then sort of the game becomes, okay, let's say the ketone really binds well, very similar to the carboxylic acid. Then you start to say, okay, now how important is sterics, right? So then you start to sort of beef up that methyl group to, let's say, an ethyl, or as a propyl or a terbutyl. Terbutyl is probably excess, but that's okay. Esters, right? They play, very similar type of roles, keeping in mind, of course, the resonance structure, being able to identify hydrogen bond donors, acceptors, so you guys see, right, that very simple sort of question that was asked in the first exam is playing a role, right, all the way through sort of the course, I would say. The other things I would keep in mind is that these are often play a big role, and we'll talk about this, maybe I think in a class or two. We'll talk about, esters end up being a really great starting point for drugs that you're going to take via mouth. And usually why that is because you can go ahead and once they're orally administered, then right, they head down right, the esophagus, right down the stomach, and then they're hydrolyzed to sort of their more active species, to carboxylic acid. So we'll talk a little bit about that as we go. Yeah. So why do these things, matter, right? So I think this is a really good example. This is still, highly debated as to, what exactly aspirin's doing, in terms of sort of acting as a COX inhibitor. And here's sort of the proposed mechanism. I think right now it's sort of generally accepted. But the idea is that, the way it performs its inhibition is actually through just functioning as sort of an acylating agent for the COX enzyme. And so, very similar type of mechanism you guys have seen, right? Serine comes in, right? The electrons go up, down, and a leaving group leaves, and ultimately left with sort of acylation of the protein, and then the salicylic acid. Now, you might say, okay, well, that's functioning then as sort of an irreversible type of inhibitor. And what I would say is that the acetyl group oftentimes is labile, right? So it's going to be a little bit challenging to, even for the protein, to keep that on there. So you can't really use it as an irreversible inhibitor. So oftentimes water will come in and sort of hydrolyze that acetyl group, and it'll generate acetic acid. And so that's where the dispute comes in, where people are usually like, well, maybe the inhibition happens because you have formation of acetic acid ultimately. But still, there's a lot of good papers on that, and there's actually like 2 prominent scientists that really sort of go back and forth on this thing. So just when you think aspirin is solved, it's not completely solved yet. Yeah, to touch base quickly, I think on alkyl halides, it's important to note, right, they can act as electrophiles. You guys definitely know that. With anything nucleophilic, they form a no covalent bond. When we talked about that, and so that was, heavily talked about sort of irreversible inhibitors, for example. The aryl halides, though, they don't do the same thing, right? It's hard to do what would be sort of the equivalent of an SNAR, unless the aromatic is poised to go through that type of process. And usually there's an alpha nitro group that you need, but you don't really need to know that at the moment. But it's not as easy. You can't really do SN2s directly sort of on an aromatic unless it's gamed a bit. And we'll talk about that as we move along. A couple other groups worth noting. Thiol groups are known generally to be good ligands for metal ions. In fact, you won't find a lot of sulfur containing drugs for the exact reason that usually, one, they bind, pretty well to metals. And then number two, they're usually easily oxidizable. So they come up and they kind of enter the body, where they come in the presence of, for example, cytochrome P450 enzyme, and they're immediately oxidized. And usually those oxidized products are not productive in creating a biological response. So, and usually those are kind of just discarded or excreted. Ethers could act as hydrogen bond acceptors. The aero variants are usually poor hydrogen bonding acceptors, and it's worth taking a minute to figure out why that is, right? And if you do the resonance structures of, let's say, phenol versus just an alkyl ether, you'll start to see why you're pulling electron density sort of away from that oxygen. And how is it usually tested? Kind of like I was saying before, it's tested by increasing the size of the alkyl groups on the ether, typically. Other groups, you're going to see some nitros and nitriles, and those are usually used, directly to adjust the electronic properties of the molecule. Usually they're attached directly to an aromatic, for example, and they're usually electron withdrawing, so they pull electron density away from it. Others may modify the molecule or conformation shape or act as sort of a metabolic blocker. We won't talk much about metabolic blockers unless we have a little bit of time later. That really could be sort of its own section, and I'd be willing to chat about that, but I'll poll you guys before we do that. Right. So this is where you start to see, if you look through all the list of drugs, right? Heterocycles are super, super prominent, right? In sort of the med chem game, right? And the reason for that, right, is that they're really great hydrogen bond donors and acceptors. And of course that, a lot of things, sort of come into play there, right? There's not only the sort of, as it sits, for example, on the slide, but then also it's sort of all of its protonated forms. So this thing is sort of an N plus. So that ends up being really important, to considerations as you sort of move through in sort of the design. So oftentimes what people will do is they'll go ahead and they'll start with, like, just, let's say if you have a phenyl substituent on your molecule, and then you put a nitrogen in the ring. Oftentimes what they'll do is they'll start to, when there's creating libraries, they'll start to move that nitrogen to other locations in the ring to see what kind of effect that has. And we'll talk a little bit about that as we move along. Right, they can be aromatic or aliphatic. I would say a majority of them are actually aromatic. I would say the aliphatic type ones are usually sort of seen in the context of sort of peptide containing drugs, and that'll be a whole nother cool section that we'll go through. Usually interact at many binding sites through a variety of bonding forces. And so just to give you an example of sort of, I think this is such an inspiring sort of look at this type of thing, right? So you can imagine, right, these blue residues, right, are sort of the binding site for methotrexate, and look at all these interactions. I mean, that happen with the molecule. You have sort of, the nitrogens in the ring, the nitrogens that's sort of outside the ring, acting as both hydrogen bond donors and acceptors. Super, super cool. And then you have sort of this peptide backbone. And oftentimes those peptide backbones are really there to guide sort of entry into or outside of a cell, for example. So, if you're wondering what all that spinach out there is for, that's usually what sort of helps the molecule get to where it needs to go. Right. So you guys obviously know the structures, right, affiliated with DNA and RNA, but it's really important to think about sort of what the tautomers look like in those structures, right? So by a tautomer, what I'm talking about is if you just take sort of T right in the top left and you move to the T on the right, it's gone through what would be sort of the equivalent of a tautomerization, right? And those are considered sort of tautomers of each other. And certain tautomers play a role sort of in the network right, that goes into sort of, strong base pairing in DNA. And so, that's represented sort of, pretty well on this slide. So they're showing sort of what are the core contributors that sort of play a role in sort of the whole, in sort of creating sort of such a really strong structure of DNA. And I think that's worth, taking a minute and sort of like digesting a little bit. Really, really sort of neat when you start to sort of consider those factors. Isosteres is another sort of space that we'll talk a little bit about as we move along. Those are atoms or groups of atoms which share the same valency and that have chemical or physical similarities, right? I won't get too hyped up on you necessarily giving a perfect isostere for sort of design of some of the compounds that you'll do. But what I would say is that it's sort of, when we're talking about sort of valency, for example, right, these generally, right, if you kind of look at, I think the good ones to really sort of appreciate this are sort of in the sort of bivalent isosteres type section, where you have sort of the ketone, then it moves to the amide, the ester, and the sulfur. Right? You can imagine for all those, very similar to like when we went through the carboxylic acids, the esters and amides, right? They all sort of, they kind of share the same valency in that, like, you'd be able to draw, let's say, the same type of resonance structures for them. You might be sitting and saying, well, how would I do that with a ketone, right? Because you don't really have like an X group, like a nitrogen or an oxygen. When they're referring to that, what they're talking about is actually what would be sort of the deprotonated form. So you imagine it sitting in sort of its enol form. So once again, tautomerization coming into play there. But then you can sort of start to really appreciate that sort of in ring equivalents, right? So the top ones in sort of the pyridine and in the phenyl group, those sit with the same number of sort of pi electrons, and very similarly on sort of the bottom ones, these 5-membered ones. I would again say the first one, the one that doesn't contain a heteroatom. Think about that in terms of its sort of deprotonated form. Yeah, so identification of a pharmacophore is going to be really important, and this is something that you're going to have to do, especially if you're an honors or graduate student, sort of in the context of the honors contract. So this summarizes the important binding groups that are required for activity and the relative positions in space with respect to each other, right? So we're really used to, looking at these molecules, whether they're stereochemically complex or not. We're used to looking at like sort of flat on the board. And while that's a really nice depiction, I would say that it doesn't completely accurately sort of represent what the pharmacophore really looks like. So these rings, for example, in one on the left for glypine, right? They're actually not all sitting in the plane, right? You can imagine that they sit sort of as I would say like sort of chair-like type structures. And so what they do is they sort of fill a space, a 3D space that's actually not just sort of a flat molecule. So you would imagine that if you just like laid this thing down on sort of on the table, right? You would imagine this thing would just be flat, right? But there's actually sort of this like sort of 18-degree type angle, right? That you need to account for in that. Am I going to ask you to predict that? Absolutely not. But I might have you, I might sort of ask you a question that sort of, gives sort of some understanding if you have a working appreciation for this. I would say to really spend some time just developing a working appreciation for that. If you Google pharmacophore map, you'll see all sorts of different ones. So I'd be happy to provide some more for you as we get closer to exam 2 time. Alkyl substituents, right? This is this is in the book. I wouldn't worry too much about, again, I'm not going to ask you like, how do you go from like the ether to how do you take the ether off? You do that with HBr and all that other stuff. You're not going to need to know that, right? So, but it's worth, I think just to have this as reference as to sort of the different types of transformations that there are, how we do it, sort of is, if you're curious. Alkyl substituents, right? These are the, I think the, underappreciated category of we'll quote unquote functional groups. They're usually right on ethers, amines, esters, amides, etc. We talked a lot about sort of, methylating or demethylating a functional group. But varying the length and bulk, right, gives an idea of the size of the binding pocket. So immediately, right, if someone knows that there's a pocket in the binding site that sort of, has some favorable interactions with an alkane, for example, a methyl, they'll immediately say, okay, well, how big is that pocket, right? They can look a bit into the model, but sometimes, right, with the sort of induced fit process, you don't really know necessarily if that is sort of representative of what of the type of molecule you're trying to design. So what they'll usually do is they'll start with the methyl, as sort of their sort of starting point, and then they'll move to a once again an ethyl, isopropyl, and a tert-butyl. Tert-butyl is not often found in drugs. In fact, I spent a lot of time trying to find a whole bunch of those, but not very prevalent. And usually, that is a remarkably bulky group to sort of fit into really anywhere. So this is sort of an exaggerated sort of version of that, of course, in the bottom. But I would say something in the neighborhood of like ethyl or isopropyl usually does sort of help with binding. Aromatic substituents. Yeah, this is one of the easiest parts to sort of functionalize, right? So you can imagine if you want to vary a structure, it's usually really challenging to modify, let's say, a very alkane containing type molecule. So, cyclohexanes that we saw before, selectively putting stuff on those is actually pretty challenging. And so I just want to give you an understanding of where sort of, why aromatic substituents are so popular in drugs. And usually that has to do with sort of what we're capable of doing sort of on the synthetic side of things. And so you guys learned in sophomore organic that there's a number of different sort of electrophilic aromatic substitutions, nucleophilic aromatic substitutions, etc. The Friedel-Crafts type reactions, right? Those things are still used sort of on an industrial scale. And so, but the other thing is, like, now there's sort of a whole host of methods that are looking to do that sort of in sort of a milder sense. I don't know if you guys got the opportunity to actually go in and run a Friedel-Crafts type reaction, but I think that'd be really cool. I don't know if COVID maybe affected that, but nevertheless, right, this is sort of what the game looks like, right? You have like sort of this pair substitution, and it's a weak bonder. So what you usually do is you sort of take the alcohol and have it sort of dance around the ring. So you'll put a substituent, for example, in the meta position, and and that's how you start to sort of feel out the binding site. Right. So it's really important to note as you go through, right, resonance structures. I would say if you approach something that you can imagine drawing a resonance structure, in particular with the aromatics, I would do it and sort of have an understanding of what sort of if that increases or decreases, let's say the potency of the hydrogen bond donation or acceptance. Yeah, extension strategies are going to be huge. Right? We get someone coming in that's going to talk about this. This is going to be awesome. So these are usually used, right, to strengthen the binding interactions and activity or receptor agonist, for example, or enzyme inhibitor. And usually what happens is you start with a drug, and let's say, okay, for example, if we want to go ahead and make, you can imagine, usually people are going after something that's like polar. Think, okay, a hydroxyl group is really common, usually helps sort of drug bind. So what we're going to do is we're going to take a hydroxyl group, and we're going to have that sort of substituent sort of all over the drug, just to sort of get a feel for where other types of sort of hotspots for binding are. Other common ones are amines and alkyl substituents. You guys saw, that magic methyl effect has actually played a huge role in this. You find actually these like discrete sort of hydrophobic pockets that are really useful to capitalize on. So these extension strategies sort of like add more to the molecule just to sort of feel out the active site. Yeah, so what do these sort of types of approaches look like? Where you usually have sort of these interactions with the binding site and sort of the top left. You start to do chain extensions, and you start to see by doing that, these are really nicely depicted. They, you're able to sort of optimize that sort of binding to sort of two spots. And then if you take it too far, right, you start to lose that sort of favorable binding of what would be the sort of the ball on the right. Another option is to either increase the size or decrease the size of a ring. Usually they'll start with something that was easy to synthesize, for example, this 5-membered one on the left. But then you start to sort of adjust where the phenyl group is if you just if you sort of tweak the size of that central ring. And that ends up playing a sort of another huge role in sort of the development of extension strategies. Yeah, right. So this is another key one, right? So if you have, something that you want to inhibit, keto reductase, for example, right? So for example, this one is capable of reducing estrone to estradiol. What you'll start to do is you start to use extension strategies that'll help reduce the activity of this enzyme by binding. And so usually how you do that is you go ahead and sort of give it a steric blocker. And so what it usually is before it didn't have sort of this alkyl group on it. And so what you do is you put an alkyl group sort of off of that. I wouldn't ask you obviously to predict this whole this whole piece out here. But for example, if you put an alkyl group right there, you've now sort of created more sterics in that area, right? And so now the enzyme is incapable of actually doing the reduction of that molecule. Pretty cool. Ring expansion. This is sort of another good example. These ones are hard to predict. So I likely wouldn't ask you something like this, but for example, in this molecule here, right, they're able to use that extension strategy, that ring expansion strategy, to sort of not only optimize the interaction with what would be the carbonyl on the left of that sort of bicyclic ring structure, but then also the carboxylic acid on the right. And then by doing that, you also are able to sort of adjust carboxylic acid all the way on the left. That's pretty challenging, but a good sort of explanation. And that was actually used right in a pharmaceutical before. Ring variations are also important. This is sort of what I was talking about from before. Increasing or decreasing the size of, let's say, an aromatic ring is definitely a completely plausible strategy for assisting in sort of binding or modifying a drug, or putting creating heterocycles right from the aromatics, right? So you can start to dance, let's say, in nitrogen sort of around the ring, and you'll get more practice about with that as we go. This is one that's been really common for these NSAIDs. We'll learn a little about NSAIDs as we get into some of the topics we're going to talk about a little later. The ring fusions. So again, we talked a little bit about sort of those rigidification strategies, and those do play a role. But I would say that sort of the ring fusions end up playing another sort of major role, right? This is if you go from the left molecule to the right molecule, right, you see that you've you've taken away hydrogen bond donors and acceptors, and then you've also introduced sort of more van der Waals interactions. So that might be another good option for you to pursue. We're gonna Well, we can quickly go through bioisosteres. Bioisosteres, right, they're groups that can be used to replace another group while retaining desired biological activity. Okay, you don't know that right until you've tested that. So, you know, a really good example was actually sort of this one in Saltapride here, where they're actually able to replace this amide with the pyrrole ring. And we'll talk later about how to, you know, how to get you ready for, you know, questions related to bioisosteres, but really sort of neat concept, right? You can sort of completely change the functional group and still end up with sort of the similar bioactivity. Yeah, so there's sort of another example right here. Take carboxylic acid to the sulfonamide, and sort of you're able to sort of introduce new types of interactions. But you know, once again, it's another type of example. And I think we'll leave you there because the next topic probably should be presented at the same time. And thank you all for attending. Have a great weekend. Live it up out there. We got another couple of weeks of good weather. Thanks so much, everybody. Have a great weekend.
Same to you, Dr. B.
Thank you.